Start recording. Okay. Make a 2-minute video that says this is stupid. Okay, so a function can be continuous for only part of its domain. That's all right. That is allowed. So a function could be continuous from the right. And the way that we say that is we denote a little plus sign next to our letter saying that the limit is this and is function from the right. It can be continuous from the left, and we use the simplification. So as long as the limit approaches and equals the function from one direction or the other, we can do continuous from one direction to the other. If it is the function. A function is continuous on all intervals if and only if at every number in the interval is continuous. So the interval you're looking at is continuous in that interval if it meets the criteria that we set out. Okay, so let's look at this example 2. We're looking at a specific interval, -1 to 1 inclusive. So show that this function is continuous on this interval. So let's take a look at if we let our value a be strictly within the. Let's just take a look at what happens if we let a be strictly inside of this interval. Then we have that the limit of x versus a of the function is to be right out of 1 minus 1 minus 6. I want you to think logically for a minute. If a is strictly less than or within -1 and 1, that means x squared will be strictly less than 1. If we let x approach a and a is strictly within, meaning it is less than the absolute value of 1, then 1 squared, if it's less than 1, will be closer or less than 1. Right? What I'm saying is, we can say 0.9, 0.999, 0.999. As long as it's strictly less than 1, then this side squared is going to be less than 1. So that means because we know that it's going to be within the restriction, I could use direct substitution. I could say the limit of x approaches a is going to be 1 minus the square root of 1 minus 8, but I could do stuff like this because I know that it doesn't violate the restriction. Okay? If I use direct substitution, then that's saying, well, that's going to give me the same number as if I just put the a directly into the function. Left side and the right side of this. So long as I'm talking strictly, it is less than or within -1 and 1. Are you following me so far? Okay, let's take a look at the end point. Let's take a look at if the limit of x approaches -1 from the right. Remember, we're looking at a number line here. So in the middle, 1 here, -1 here. We are interested in the interval inclusive -1 to 1. So I'm only interested in the limit as it approaches -1 from the right. As it approaches +1 from the left. So if I approach -1 from the right, then because I'm within the limit, -1 from the right. Could use direction. Because I'm using the and I'm not violating the receipt. Because I know that this is representing F that is close to -1 from the right. So if it's -1 squared, this will give me 0 here. I could do that. But yes, that's an inverse. And then I test the other end. Limit and test approaches +1 from the right. As before, getting infinitely close to this function, I know that at 1 it doesn't violate any kind of restriction and it is within our domain. So I could use the rest of the again. 5 minus square root 1 minus squared also gives this. So I can say therefore left hand limit equals the right hand limit and this equals the function at the middle. So it is so for any point within -1 and 1, I'm allowed to use the direct substitution is defined, will violate restriction. Then I test the endpoint. Usually the endpoints are continuous. So we have a function that is continuous on the interval measure. Let's do it. Okay, if we have two functions, f and g, and they are continuous at a, we're going to let c represent constant, then the following are also continuous. Essentially all of them. With the exception of number 5, where even if it is defined, if it is defined with 0, then, sorry, if it is defined and the function is 0, as long as the g function actually is not 0. In the disjunctive continuous, as long as we have a denominator. Okay, another point here, any polynomial is continuous on all of them. Any rational is continuous wherever it is defined. As long as not hitting the restriction, we're good. So let's take a look at the bottom here. What is my restriction? It is 5 minus 3x cannot be 0, so x cannot be -3. 5 over not more. Positive 5 over. Right? So this is my restriction. If I'm looking at the limit, see, as x approaches -2, this is not my restriction, so I can use direct substitution because I know it's going to be continuous because of what we just read up to. Okay, so I could just use direct substitution to 1, 5, 2, but we just popped it. The 1, bottom. Okay. So as long as the point of interest is not part of my restriction, I can use the rational So like the one that we just did, and polynomials are completely everywhere, but there is not. I pointed in such a negative 2 minus 15 is not the same. Okay, last example, last box of importance. The following types of functions are continuous at every number point in their domain. Rational, polynomial, metric, English, they are continuous at every number in the domain. So, where is the function log x plus inverse tan x over x squared minus 1 continuous? In other words, first, let's look at denominator. What would make the denominator 0? Positive or negative 1. So we cannot be a positive negative 1. Okay, what would make log x not be usable? Or what is the domain of log x? Remember what an exponential looks like? The log is the inverse of an exponential, and we put over the y equals 1. Tan is equal to 0. This is about 10. Again, think of a picture. What does the picture of tan look like? Kind of like that, right? Tan inverse means I flipped it on its side, so what does it look like now? Yeah. Yeah, so what's my domain? It's all real. Remember, inverses are taking our original functions and reflecting them over the y equals x naught. So here are my 3 restrictions. So let's talk about overall. Where is it continuous? What is the domain of this function? Okay, so it's got to be greater than 0 and cannot be equal to 1. Can you tell me how to write this in implementation? So you write it 0. Third bracket 0, comma, and 1, 1. So third bracket, third bracket. Well, capital, yes. There you go. Okay, so remember when we have functions that we're putting together, we're looking for overlapping domains. And where's the continuous and where x does not hit any of the restrictions. So we're treating each individual piece as its own thing. What is the domain of each piece? Where do they overlap and come together because we're putting these functions together? Tan doesn't give us any information at all. Log tells us it has to be positive, and the denominator says it can't be 1. So it's all positive numbers except 1. So I have to start at 0. I have to use a curved bracket so that I'm not including 1. And I use an intersection to say between 0 and 1. Between 1 and 1. How are you feeling about it? Kind of comfortable? We have 30 minutes. This is an excellent amount of time. You have lots of questions there. You've already done 2 of your homework questions. Here's your homework assignment. I also have practice problems listed on Delta Math Business versus